Welcome to sections 2.6 and 2.7. We'll be tackling these sections together in conjunction with each other because their topics are very much related. In these sections, we're going to be talking about the concept of the inverse of a matrix and the concept of elementary matrices. So we're going to introduce some terminology, do some examples, see how these objects work together. So to start off, we're going to just come right out and define the concept of the inverse. So we let A be an n by n matrix. So this is a square matrix whose number of rows and columns are the same. If there is another n by n matrix B such that A times B equals the identity matrix, and alternatively B times A equals the identity matrix, we call B an inverse of A. And in this case, we say that A is invertible. So a matrix is invertible if it has an inverse. So it has another matrix that when multiplied by it, they essentially, for lack of a better term, cancel each other out or like undo each other. They turn each other into that identity. Note, when we're talking about like matrix algebra, the concept of division is not something that we use for matrices. So this doesn't mean B equals 1 over A. So when you think of an inverse like in algebra, you think of, like 2 and 1/2, like a reciprocal like that. It's not the same thing with matrices. With matrices, the inverse does have a similar effect where when multiplied together, they give us the matrix equivalent of 1. That's the identity matrix. But it is not the same thing as dividing by A. So we know that a matrix is invertible if it has this other matrix when multiplied gives us the identity. The next question, can an invertible matrix have two inverses? Can there be more than one inverse for any given invertible matrix? So let's go ahead and prove whether or not this is true. So we're going to suppose A has two inverses. Those will be B and C. Then, if A and B are inverses, A times B must be equal to the identity matrix, which is equal to B times A. And since A and C are inverses, they multiply to the identity matrix in both directions as well. So, if we start with B on the left-hand side here of this equation, B is the same thing as B times the identity, right? Because anything times the identity is just itself. And now we know that the identity is equal to AC, like this. So we can go ahead and make this B times AC. We know from properties of matrices that we can move these parentheses around. So we can regroup the B and the A together times C. And BA, because they are invertible matrices, that equals the identity again. So this would be equal to the identity times C, which is just C. So if we assume that A has two inverses, B and C, what we just proved is that those two inverses are equal, meaning that they're actually the same matrix. So it's not two different matrices, it's actually just one. So thus, an invertible matrix cannot have two inverses, so it must only have one. All right, so every matrix that is invertible will have only one exact inverse. And this unique inverse of the matrix A, if it exists, is written with this notation. So it looks like it's a to the negative 1 power. Again, don't get that confused with like a negative exponent. This is just a notation to signify that we're taking the inverse. It doesn't mean to the negative 1 power. Now, one of the primary uses of the inverse is the inverse matrices can actually help us in solving linear systems. So if we were asked to solve a times x equals b, so those systems like we've seen in the previous sections, if we were asked to solve this for x, if a is invertible, we could multiply both sides of this expression on the left-hand side by A inverse. A inverse and A would turn into the identity and would be gone, and on the right-hand side, we would be left with this. So if we know that a matrix is invertible, we could find the inverse and then just multiply that by this b vector to solve for the x vector. So this does give us a method to be able to solve linear systems if we can find what the inverse is. And that's something that we're going to be talking about a little bit later. So consider the following matrices. Look at a couple examples here. The zero matrix, so the n by n, the square zero matrix. This matrix is not invertible. And if you think about why that is, zero matrix with its inverse, so times whatever that inverse would be, they would have to multiply to the identity matrix, but the zero matrix times anything is going to be zero, right? It's going to be the zero matrix again, not the identity. You can never multiply the zero matrix and get out the identity, which means that you're never going to have an inverse for the zero matrix. So zero matrix is not invertible. For an example like this one, the question is this one invertible? Well, let's check. So if we took the matrix 1, 3, 2, 6 and multiplied it by some unknown inverse, A, B, C, D, the question is, could we get that to equal 1, 0, 0, 1, that 2 by 2 identity matrix? If we go ahead and perform the matrix multiplication on this side, so we go the 1, 1 position, right, and then the 1, 2 position, and then 2, 1, and then 2, 2, go through that whole process, we get A plus 3C, we get B plus 3D, 2A plus 6C, and 2B plus 6D. And we're wondering if we can make that equal to the identity. Now, if we just look at a couple of these components, so like this one, we have A plus 3C equals 1. And then if we look at the 2, 1 component, 2A plus 6C equals 2. But this expression equals 2. What am I saying? Equals 0. But this expression, if you simplify, that gives us A plus 3C equals 0. But A plus 3C is supposed to also equal 1. And this gives us a contradiction, so this is not possible. You can't have two values added together that give us 1, and the same two values added together also give us 0. So this contradiction tells us that this matrix can never be equal to this one, which means that this relationship cannot happen for this given matrix. Or in other words, this matrix is not invertible also. Now, this method of checking to see whether a matrix is invertible, it is effective, but we would rather be able to work to find other ways of testing invertibility and ultimately finding the inverse of a matrix. So that's the next couple of questions that we're going to seek to answer here. How do we determine if A is invertible, and how do we find A inverse if it is? So for 2 by 2 matrices, we have a pretty specific process here. We say A is invertible if and only if AD minus BC is not equal to 0. Right, so for the matrix ABCD, like that. So AD minus BC. If that difference is not 0, the matrix is invertible. If that difference is 0, the matrix is not invertible. So if it's invertible, then the inverse, the general formula, is going to be 1 over AD minus BC, and you can see maybe why that needs to be non-zero now, times the matrix D, negative B, negative C, A. So a 2 by 2 matrix is invertible if AD minus BC is non-zero, and if it is invertible, this is the formula for its inverse. We can verify this. So if we take 1 over AD minus BC times D, negative B, negative CA, times the original ABCD, that's going to be 1 over AD minus BC. If we do the matrix multiplication, so we get D times A minus B times C. So that's going to be AD minus BC. The second component, that's DB minus BD, which, of course, that's BD minus BD, so that's 0. Third component, that's negative AC plus AC, so that's 0. And the fourth component, that's negative BC plus AD. So I'll just rewrite that as AD minus BC again. And we can distribute this fraction in to every single component within the matrix. The zeros are unchanged, but these terms become ones. So we get 1, 0, 0, 1. So we get this matrix times this one gives us the identity, which is exactly the condition that is necessary to prove that two things are inverses. And you'll see often if we're trying to show that two matrices are inverses of each other, this is the method that we'll use. We'll multiply them and see if they give us the identity or not. Now consider the example that we just did on the bottom of the previous page. We had the 1, 3, 2, 6. We showed before that it was not invertible, but we can do so even faster now. Just take AD minus BC. So that's 1 times 6 minus 3 times 2. So that's 6 minus 6, which is 0. Which, of course, means that it is not invertible. So this general formula does give us a nice, straightforward way to determine whether a 2 by 2 matrix is invertible, and we have a nice, concise formula to find that inverse. Now, as soon as we move above 2 by 2, the process gets a little more complicated. So in order to determine the inverse for a 3 by 3, 4 by 4, etc., larger matrix, we need to use what are called elementary matrices. These elementary matrices are obtained by applying one ERO to the identity matrix. So, for example, like this matrix down here, determine whether each of these are elementary matrices. You can see we have 0, 1, 0, 1, 0, 0, 0, 0, 1. This one is an elementary matrix. Notice if these two got switched or permuted with each other, that would be the identity matrix again, right? With the 1 here and a 1 here. So, yes, this is an elementary matrix, and we find that by perform P12 on the 3 by 3 identity matrix. For this one, the question is, can we get that 7 using one ERO? And we can. We can take the second row times 7 added to the first row. So this one, yes, is also elementary. And we perform A21 times 7 on the 2 by 2 identity matrix. And then we have this one. This one initially might look promising because it's got the main diagonal here. The problem is the fact that this is multiplied by 2 and this is multiplied by 3. So no, this one will not be elementary. And the reason is we must perform multiply 2 by 2 and multiply 3 by 3 on that identity matrix. So in order to obtain this result, you would have to apply 2 EROs in order to get this from the identity, which by definition means this cannot be an elementary matrix. So when it comes to using elementary matrices, these are what we're going to be able to use to find inverses. So we say that A is row equivalent. A is row equivalent to B, which notationally is written A with kind of a squiggly arrow with the word row over it, pointing to B. So this is A is row equivalent to B. If there exist elementary matrices, E1, E2, all the way up through EK, such that when multiplied by A, that equals B. So essentially what the elementary matrices are doing, and we'll talk about this as we go through this process, but the elementary matrices each represent an ERO that is being performed on A. So this is basically saying take A and perform this ERO on it, then perform this ERO, the next one, the next one, the next one, the next one, and just go through that whole process of performing EROs until we get to B, the desired result. Now, if this relationship were to hold with the identity, so if A is row equivalent to the identity matrix, then that means all the elementary matrices applied to A equals the identity. So this group of matrices here times A is the identity, which means that this group of matrices must be the inverse. Right? And that because that's what the definition of the inverse is, right? Any matrix times another matrix that gives the identity, they are inverses of each other. So this set of matrices gives us A inverse. Now, these matrices are essentially just single applications of EROs. So what we're going to be able to do is we're going to be able to start applying EROs to an identity matrix. and ultimately end up with a inverse. So how is this going to work? Well, our process is as follows. So we're going to form the n by 2n matrix A with the n by n identity. So I have the augmentation bar here because you're going to have two matrices that are n by n being kind of stuck together within one just really big matrix. And this is so that we can keep track of both of them at the same time, because we're going to be applying EROs in step 2 to both sides of this big n by 2n matrix. So we start with A augmented with identity. We perform an ERO. That gives us E1A and E1, right? E1I, we don't need to write the I there. And then we apply another ERO, and we would get E2, and then still E1 and A, and then E2 and E1. And we would keep doing this for as many EROs as it takes. And on the left-hand side, so we'll have EK all the way down to E1 times A. And on the right-hand side, we'll have EK all the way down to E1. This object on the left-hand side, that's this right here. That is the identity matrix. That's what we just showed up there. So this side, this is the identity. And this side is all of those elementary matrices. That is A inverse. So this side is A inverse. So this gives us a nice clear-cut procedure for finding the inverse of a matrix. All we need to do is we need to augment the original matrix with the identity, perform EROs until the left-hand side is the identity. Once that has happened, the right-hand side automatically will be A inverse. Okay, so we start with the original and identity. Once we get it to the identity and another matrix, that other matrix is the inverse. This is often referred to as the Gauss-Jordan method. So if you see questions asking you to apply the Gauss-Jordan method, this is what it's asking you to do, essentially to perform EROs on an invertible matrix until we reach A inverse. So let's try this out. So find A inverse given that A is this 3 by 3 matrix. So we're going to take that matrix, so 1, 0, 1, 0, 1, 1, 2, 3, 6, and we're going to augment it with the identity matrix of equal size. So we have a 3 by 3 and a 3 by 3. And now we're going to start performing EROs. Our focus while we're performing the EROs is to turn this matrix into the identity matrix. Okay, so that's our ultimate goal. This one, we're going to track the same changes as we go through this process. And once this one becomes the identity, this one, whatever it is, will be the inverse. Okay, so let's see. We have a pivot right here. We've got a 0 here, but not down here. So let's go ahead and add 1 to 3 times -2 to clear out this 2 down here. So that's 1, 0, 1, 0, 1, 1, 0, 3, 4. And then apply the same ERO to this side. So that's 1, 0, 0, 0, 1, 0, -2, 0, 1. This is a time when it is particularly important to keep track of your EROs very carefully, because it's very easy to misplace a number or to skip a row by accident or to apply it to the left-hand matrix but not the right-hand matrix. So very important to exercise caution when going through these problems. Next up, let's see. We're going to need to get rid of this 3, right? We have our pivot right here. So let's go ahead and add second row to third times -3 to get rid of that. So we're going to add 2 to 3 times -3. So we get 1, 0, 1, 0, 1, 1, 0, 0, and that works out to a 1. And do the same thing to this matrix. So 0, 1, 1, 0, 1, 0, excuse me. Add 2 to 3 times -3. So that's -2, -3, 1. And we are almost there. On this row, so on this side, we have the main diagonal is all 1s. That's good. We've got 0s here and here. We need to get rid of these 2. So let's go ahead and use the third row, multiply by -1 and add to 2. And we'll also multiply by -1 and add to 1. So we'll do 2 EROs here. So we'll add 3 to 2 times -1, and we'll add 3 to 1 times -1. On the left-hand side, we have the identity matrix. On the right-hand side, let's see what we get. So we have -2, -3, 1. Multiply this by -1 and add it to here. So that's going to be 2, 4, -1. And then do the same thing to the first row. That's 3, 3, -1. And now we've reached this point. This left-hand matrix is the identity now, which means that this one must be the inverse of the original matrix. So A inverse is 3, 3, -1, 2, 4, -1, -2, -3, 1. So this is the process that we have for finding the inverse of a square invertible matrix A. Now, we had talked a little bit earlier about the idea of these matrices being able to help us solve linear systems. So here's an example right here. If we take a look at this linear system here, let's turn this into a matrix of coefficients. So like let's put it in this form, this AX equals B form. So let's see, that's going to be 1, 0, 1, 0, 1, 1, 2, 3, 6, multiplied by XYZ equals 7, -1, 2. Right? And if we were to perform the matrix multiplication on all of these, we would get exactly out these 3 equations again. So it's all equivalent. It's all the same. The nice thing for us is that this matrix of coefficients is the same as the matrix we just worked with here. So we know it's invertible. We know that it has an inverse, and we already found that inverse. So we know that X is equal to A inverse times B. So XYZ is equal to 3, 3, -1, 2, 4, -1, negative 2, negative 3, 1, times 7, negative 1, 2. And if we go ahead and perform this multiplication, we go first row, first column. So that's going to be 21 minus 3 minus 2. So that's 16 for the first component. We go second row with the column. That's 14 minus 4 minus 2 is 8. And we do third row with the column. That gives us negative 9. So we have x, y, z equals 16, 8, negative 9. If you go component by component, that tells us right there. X is 16, y is 8, z is negative 9. So x is 16, y is 8, z is negative 9. So the solution to this system of equations is just this one point, 16, 8, negative 9. And remember, we looked in the previous section at the concept of the number of solutions to a linear system. And it can either have one, infinitely many, or none. And this is a case where it has one, and exactly one solution. And we can find that solution using the inverse of that matrix of coefficients. The matrix is going to be, the inverse matrix is going to be a major topic of conversation for us throughout linear algebra. Invertible matrices have a lot of properties that are very useful to us. We're going to look at a bunch of them in the upcoming section 2.8, and we're going to see how we use them throughout future chapters as well. So let's go ahead and take a look at section 2.8. This section covers the invertible matrix theorem. So the invertible matrix theorem is a very big theorem with a lot of equivalent statements that all give conditions for a matrix to be invertible and equivalencies to that. We have, you can see right here, A through F right now. As we go through more chapters throughout this course, we're going to develop more and more equivalent statements that are compatible with the statement A is invertible. And we'll see, we're going to run our way through a lot of the alphabet by the time we get done with the course. But there's a lot of statements that we can use interchangeably with invertibility. So let A be an n by n matrix. The following are equivalent. So A is invertible. Okay, so again, there exists a matrix that is A inverse, where it has this relationship, right? AB equals the identity. This is equivalent to saying the equation AX equals B has a unique solution X for every B, right? And that's kind of what we just solved for. So if we find a solution, one unique solution to a system like this, that means that A is invertible. If the equation AX equals 0 has a unique solution, specifically the 0 vector, or just all zeros, then that is the same idea as part B. So if this has that one unique solution of zeros, then that also gives us invertibility of A. This type of system in particular, this is one that we're actually going to deal with a lot in future chapters. This one is called a homogeneous linear system. So a homogeneous linear system is a linear system just like this general one that is specifically equal to 0 or equal to that 0 vector. So, and again, we'll talk more about these in the upcoming chapters, but that's just a linear system that is equal to this 0 vector. Another equivalent statement, the rank of A equals n. So we have an n by n matrix. If the rank of A equals n, that means that the number of rows and columns that have pivots is n. So in other words, every column has a pivot, or every row has a pivot. Okay, so there are no free variables in that case, right? There are no free variables. Yeah, no free variables. It's only the leading variables that gives us, right, the back substitution, which we can then use to find one unique solution. It's all linked together. A can be expressed as a product of elementary matrices. So that was the process that we talked about in invertibility. And A is row equivalent to the identity. So again, very much involved with that same process that we were just looking at in the last section. So all of these statements are equivalent. If any one of these statements is true, all of the others must also be true for that specific matrix A. All right, so this can be useful then. If we know A is invertible, we know all of these things about the linear systems, about the rank, about the elementary matrices, all that kind of stuff. But that also means if we can find systems like this, or if we can look at the rank, or we can look at the elementary matrices, all of these can tell us if A is invertible or not. So this becomes a valuable tool when testing for invertibility. So let's take a look in this section. We're just going to look at a couple different like theorems and properties and actually go about proving these, kind of put our inverse matrix stuff to work. So first one here, if A and B are n by n invertible matrices, then AB is invertible and AB inverse equals B inverse times A inverse. So we've got two invertible matrices of the same size. AB is invertible, and this is the relationship between the inverse of the product and the individual inverses of B and A. So if we want to show that two things are inverses of each other, the best thing we can do is multiply them together. So what we're saying with this statement is that the inverse of this expression is this expression, right? That's what we're saying. AB inverse is this. So if we want to show that these two expressions are inverses of each other, we can multiply them together and see if we get the identity. If we multiply to the identity, they are inverses. If they don't, then they're not. So we'll start off AB times B inverse A inverse. We can go ahead and regroup parentheses. So I'll go ahead and regroup around the middle two. Now this expression, B times B inverse, any matrix times its own inverse is the identity. And any matrix times the identity is just itself. So we don't need to show the identity here. So that's just A times A inverse, which of course by definition gives us the identity. So this one times this one gives us the identity. And if we go about it from the other direction, so we switch the order of multiplication, we can see a similar process unfolding here, but we get A inverse times A, which yields the identity, which gives us B inverse times B, which also yields the identity. So AB times B inverse A inverse is the identity matrix, and B inverse A inverse times AB is the identity matrix. Thus, AB inverse equals B inverse A inverse. So, and it's like I said, when you're trying to show that two things are inverses of each other, oftentimes the quickest and best solution is going to be multiply them together and show that we get the identity from both directions, right? A times B and B times A, so to speak. And then let's look at this next one here. So if A is invertible, then A inverse transpose equals A transpose inverse. So essentially showing that the inverse and the transpose can be performed interchangeably. Like you can perform the inverse first and then the transpose, or the transpose first and then the inverse. So again, we'll use a similar reasoning here. This says that A transpose inverse is this expression. So if we're trying to show that these two are inverses of each other, we simply need to multiply them together and see what we get. So we're going to have A inverse transpose times A transpose. It is a property of the matrix transpose, if you remember from earlier in the chapter, that it distributes across. So we can go ahead and pull it out of both, like that. So that is A inverse times A, all transposed. A inverse times A is the identity, and the transpose of the identity is just the identity. So it does not change by being transposed. So that's good. And if we take the multiplication the other way, A transpose times A inverse transpose, again, the same matrix property holds. We can pull the transpose out of there. So that's A times A inverse, all transposed. So that's once again identity transposed, which is identity. So by taking this term times this one, both left-hand multiplying and right-hand multiplying, we get identity both times. So thus, A inverse transpose equals A transpose inverse. And that general principle that I've been talking about, right, is noted down here at the bottom of the page. So in general, to prove the two matrices are inverses of each other, multiply them together to ensure that the identity matrix is obtained. And that brings us to the end of chapter 2.